All right, next up is question number 9 that says, let E be the portion of the solid sphere which consists of all points rho, phi, theta, where rho varies from 0 to 2. So in other words, this is just the solid ball of radius 2 centered at the origin that lies between the cones phi equals pi over 4 and phi equals pi over 3. Suppose the mass density delta measured in kilograms per cubic meter at a point in E is inversely proportional to the square distance from that point to the origin. Find the total mass of E. All right, so first, let's just draw a picture of the region, and we'll start with the sphere. So this is just our sphere of radius 2 centered at the origin. And then we'll put in our cone. This is just same cone from 8 part B, right? Phi equals pi over 4. And then for phi equals pi over 3, be a little careful here. Remember, phi is being measured from the positive z-axis. So we're going to rotate pi over 3 radians from the positive z-axis there. So it's actually going to look like this. And then we want the region inside the ball and between these cones. So we're looking at this region here, E. Okay, cool. So now for the mass of our solid, this is going to be the triple integral of our mass density function delta over our region E. Okay, so the things to sort out here are one, what are the bounds? And so set this up as an iterated integral in spherical coordinates, and the other thing to sort out is the density function delta. Okay, so let's go ahead and set up the bounds first. So if I'm thinking about letting my radial distance rho vary first through the region, well, I'm going to start here just at the origin, and then I'm just going to range out to the edge of the blue sphere there. So in other words, for a fixed phi and theta, rho will vary from 0 to 2. Okay, so for bounds here, I'll make a little space, but bounds for rho would just be from 0 to 2. And then for phi, well, we're going to just think about the portion along the red cone, phi equals pi over 4, and then we're going to have to rotate through up until we get to the green cone, which is at phi equals pi over 3. So in other words, our bounds there for phi are just from pi over 4 to pi over 3. All right. And then lastly, for theta, well, to capture the entire region E, we're going to have to do a full 360-degree rotation there about the z-axis. So in other words, theta is going to range from 0 to 2 pi. All right. And now for delta, we're told that the mass density at a point in E is inversely proportional to the square distance from that point to the origin. And now the distance itself from the point to the origin is just rho in spherical coordinates. So the square distance would be rho squared, and delta is inversely proportional to the square distance. So in other words, our mass density function delta will be some constant k divided by the square of rho. All right, so now here's what we're looking at. Our delta is k over rho squared, and our differential volume element in spherical is rho squared sine phi d rho d phi d theta. And notice now we see that the rho squareds here are going to drop out, which is quite nice. So in fact, we're just looking at integrating k sine phi. And now we can go, oh, sorry, it's not a phi there. That's a phi. Cool. k sine phi. So let's go ahead now and compute. Now for the rho integral, k sine phi is independent of rho, so we're just going to get rho and then evaluate from 0 to 2. So in other words, we're just going to get 2 times k times sine phi. Okay, so that part's pretty nice. And then the 2k can come out front, and the integrand here, sine phi, is independent of theta, so as usual we can go ahead and, if we like, as a simplification step, just break this up. And so we're just integrating sine phi from pi over 4 to pi over 3. Okay, so we're going to get 2k. The theta integral is going to contribute a 2 pi. And then this integral is going to contribute a, well, minus cos phi evaluated from pi over 4 to pi over 3. And this is going to give us 4 pi k. And plugging in pi over 3, well, the cos of that's a half, so this is going to be minus a half. And then cos of pi over 4 is root 2 over 2, and we're going to get a minus root 2 over 2, so in other words, a plus root 2 over 2. And so here I'm going to get a root 2 minus 1 all over 2, but this 2 down here in the denominator can simplify with this 4, so altogether we'll get 2 pi k times root 2 minus 1. And as far as the units are concerned, well, delta is measured in kilograms per cubic meter. Our differential volume element would have units of cubic meters, so that product is just going to tell us the mass in that little differential region, which would have units of kilograms, and so we're summing those up, so this would have units of kilograms. So this right here is the mass of our solid, and that's going to do it. Thanks.